Let's now turn our attention to the technique called naive Bayes, which is a modification of the exact Bayes approach, and we'll see why it works. Not to be confused again with the naive approach itself. In the naive approach, we just go by the majority class. Naive Bayes is a simplification of exact Bayes. When you don't have enough data to carry out an exact Bayes analysis, then we turn our attention to naive Bayes. Okay, so we've got this scenario. Earlier we talked about this. We had two predictors, country, gender, and then given that we were able to calculate the probability of buyer and non-buyer. So the question is, why is it that this has 6 rows? Okay, that is because the country predictor has 3 possible values, Canada, US, Mexico, and the gender predictor has 2 possible values, male and female. And if you put the two together, you get a total of 6 choices. Okay, there are 6 combinations possible of the predictor attributes. Remember, they have to be categorical in order to apply naive Bayes. Okay, so let's say that you have this scenario. Can we think of 2 more variables or attributes to add as predictors? Can we think of 2 more predictor attributes? Well, we can easily think of several predictor attributes, right? For example, you can think of race, hair color, eye color, education level, income, height, etc., etc. We can think of many predictor attributes. Okay, let's say we just added, of course, let's not use these. If these are numeric, we cannot use them because everything has to be categorical in order to apply for this. Okay, so now suppose we added eye color, and there are 3 possible combinations of eye color. And let's say we add also education level, for which there are 5 possible levels, right? So then we've got 3 country times 2 gender, 6, times 3 eye color, 18, times 5 education level, for a total of 90 different combinations. Okay, so you have 90 different combinations, and for every combination you want to have a reasonable number of cases so that any predictions you make from that is reasonable. If the number is too small, then your predictions won't be reliable, right? So what you're seeing here is that as you keep adding more and more attributes, the number of different combinations tends to explode. Okay, so let's take a concrete example to illustrate what's going on here. Okay, so let's say that we are thinking of flying from Washington, D.C. to the New York area. Okay, and we have a choice. Let's say we can fly or we can take the train. We can do one of these 2 things. And let's say we are trying to make a decision. And of course, our preference is to take a flight, let's say. But we want to know for a given set of characteristics whether a flight would be delayed or not. Okay, so let's say we've got this data set with us, right? So we're looking at this data set in which we have a column called carrier, which indicates the airline. And then the remember, in naive Bayes or in exact Bayes, all attributes have to be categorical or factors, right? So we've taken the departure time of the flights and put them into individual blocks, right? So midnight to 1 o'clock a.m. is one block, 1 o'clock to 2 o'clock is another block, 2 to 3 is another block, and so on. So that is what departure time block is. So we are not dealing with exact departure times, but simply in the hour in which the departure occurs. And then we've got the destination airport. There are 3 airports, JFK, LaGuardia, and Newark. And then you've got the origin airports, which is there are 3 airports in the capital area, Baltimore, Washington International. Then you've got the National Airport, DCA, and then we've got IAD, which is the Dulles Airport, right? So there are 3 possible origins and 3 possible destinations. And the column called weather says whether there were any adverse weather conditions at the time, at the hour of departure. 0 means weather was normal, there was nothing untoward. 1 means there was some problem, right? Some weather issue, let's say snow or high winds or very heavy rain or something like that, which could cause some problems for the plane taking off. And then this is day of the week, which is 1 through 7. And then finally, the status of the flight. Was that flight on time or was it delayed? Okay, so the point here is, given the values of these attributes and given this data set, we want to build a model to determine whether the flight is going to be on time or delayed. And of course, this data you're seeing here is historical data. Using historical data, we want to build a model which we will then apply going forward. That's the idea here. Okay, and let's say that in our data file there are about 2200 cases available. Looks like a fairly large data set. 2200 rows are available, and these are the different attributes. Okay, so let's consider this. Day of the week, these are all the predictor attributes, right? So given the day of the week, the departure time block, origin airport, destination airport, carrier, and weather, given all of these predictor attributes, we want to determine what is the probability of the flight being delayed. Okay, so that's what we are trying to do here. Now let's look at some issues here. Okay, so let's say for a particular flight, we are concerned about a flight leaving on Monday at 3 p.m. So it falls in the time block of 3 p.m. to 4 p.m. Let's say the origin is the national airport. Let's say destination is our Newark airport. And let's say the carrier is United Airlines, and there's no weather condition, meaning the weather is fine. So all we have to do is we can use exact base, right? So we can simply go into this data set and locate all the rows that satisfy that particular condition that we just had, like Monday, 3 p.m., DCA to Newark, etc. The carrier being United. We've got all the attributes. So all we have to do is to go into this data set, locate all the rows that match exactly those attributes, and then out of that, see what proportion is delayed or not delayed. Simple. We can apply exact base. Just look up the table for this combination, and looking up the table for this combination is no big problem. Once you're given the data set, we can use any computational technique very easily to find out how many rows match that condition, right? So for example, we know how to do this with dplyr. We've learned how to do that. And then out of those, let's say there are 50 such flights which match our conditions in our data set. All we have to do is to find out what proportion of those 50 were delayed. And that gives us a probability for delay. Very simple, right? We can do that. But let's say we look at the data and you find that in your data set, there are only 3 matching records for that combination. And out of those 3, all the flights were on time. Now, can we come to a conclusion based on this that the probability of a delay is very low? We cannot, because there were only 3 matches. If instead these were 50 matches or even 30 matches, then you could have said, yeah, that's a large enough number. But with 3, we can't really do anything. Okay, so we're really back to square one on this. Okay, so let's exactly look at what happened. I thought our data set is quite big, 2,200 rows. So that's a big data set on which to make a decision. But let's see what happens here. There are 7 possibilities for day of the week, 18 departure time buckets in our data set. It's not 24 because maybe there are some times during the day when flights don't take off or land. For example, in the DC airport, it may not be allowed for flights to take off beyond a certain time or take off early. Okay, origin, there are 3 possible airports. Destination, there are 3 possible airports. The carrier, there are 8 carriers in our data set. And weather has 2 possibilities, 0 or 1, right? So what is the total number of combinations of the predictor attributes which are possible? Well, it turns out if you multiply all of these, it turns out there are 18,144 distinct combinations, and our data set has only 2,200 cases. Suddenly the data set 2,200 that looked like a large data set looks puny in comparison with the number of possible combinations that you have, right? So clearly that's the reason that we saw only 3 cases matching our conditions, right? 3 p.m. United Airlines going from DCA to EWR. We saw only 3 rows matching the condition. Initially that looked like an aberration because our data set seemed large. But looking at the number of possible combinations, we were even lucky to have found any rows at all, I would say. Okay, so this is the problem. Okay, so we call this problem as the curse of dimensionality, right? When you add more and more attributes, the number of potential combinations of the predictor attributes keeps on growing, and therefore we may not have enough combinations for a particular set of attributes that we are looking for. For a particular combination of attributes we are looking for, we may not find enough rows matching. In fact, our data set may not even have a matching row at all. Okay, so given that that is the case, we run into this problem. Okay, so we cannot apply exact Bayes. We could have applied exact Bayes if our data set was very large. So instead of 18,000, for the 18,000 combinations, let's say we had a data set that had some 250,000 rows of data. Okay, and every possible combination of our predictor attributes was covered in something like 50 cases each, at least minimum, right? Then we could apply exact Bayes, right? But in the real world, you don't get data sets in which there is a guarantee that all combinations would be properly covered. And this is what is called the curse of dimensionality, right? So you end up with so many different possible combinations, and even with a very large data set, the number of cases that fall into each cell may still be too small to make a prediction.